Now let's talk about exponential growth and decay. This has a lot of applications in science, particularly physics, and economics, population studies, etc. Now suppose you have a problem that says the rate of change of y is proportional to y. Reading this mathematically, when you see the rate of change of y, you are going to think dy dt. That's the rate of change. Rate means dt. Is always, of course, equals, and proportional to y, you have this ky. That's your proportionality constant, and this is your variable. Now let me solve this. Suppose I have dy over y is equal to k dt. All right, let me integrate. So the natural log of y is equal to kt plus c. That's pretty easy. Now I'm going to raise both sides to the e power. So I have y is equal to e to the kt plus c. Oh, but another way to write that is e to the kt, e to the c. But this is just a big old constant. So let me write that as capital C, e to the kt. So whenever you have a problem of the form, the rate of change of y is proportional to y, you know you have a solution that looks like that. Now, that's the basis behind Theorem 6.1, the exponential growth and decay model. C is your initial value. Let's look at what is y when t equals 0. Well, that's just c e to the 0, or just c. So if I ever have an initial amount, that's what I'm looking for. K is my proportionality constant. And if k is positive, we're going to have some exponential growth. If k is negative, we're going to have decay. There's something else that we tend to want to look at, and that is the half-life. And we'll do one of these. If I tell you the half-life of something is t1/2, that tells me that is the time it takes for this material to go to 1/2. So my y for time of 1/2 is going to be 1/2 my initial c. Real quickly, let me show you how to do this. If you've got, this is my time and this is my y value. All right, I can plug this into this equation. Y is 1/2 of c. That's c e to the k half-life. You're going to see my c's cancel. So I have 1/2 is equal to e to the k times my half-life. Let me take the natural log of both sides. So the natural log of 1/2 is going to equal k times my half-life. So in physics, you probably are going to see this formula. And you're going to see it in the form t of 1/2 is equal to the natural log of 1/2 divided by k. But this is where it comes from. Now, we can use this in solving problems where we only have 2 points. Suppose I tell you that the rate of change of y is proportional to y. So you know immediately you can write the equation y equals c e to the kt. When t is 0, y is 2. So I'm going to put my points over here. 0, 2. When t is 2, y is 4. All right. What is the value of y when t is 3? So I want y when t is 3. Okay. First thing, let's start with 1 point. At 0, 2, let me see what I get. When I plug in y is 2, that is equal to c e to the 0. So that tells me c is equal to 2. I can immediately rewrite my equation. So this becomes 2 e to the kt. All right, that's all I've done is plug it in. To find k, I go to my next point, 2, 4. All right, in this case, y is 4 is equal to c, which is 2, e to the k, and my time is 2. So I've got 2 is equal to e to the 2k. Take the natural log of both sides. So I have the natural log of 2 is equal to 2k. And that tells me k is a natural log of 2 divided by 2. Now, for simplicity's sake, I'm going to go on and find a decimal. That's 0.3466. And you'll see I carry this at least one decimal beyond. All right, so now I can rewrite this equation as y is 2e to 0.3466t. Now I want to find y when t is 3. So y when t is 3 is equal to 2e to 0.3466 times 3. So I get an answer of about 5.657. Now is where I round to 3 decimals. Always carry extras during your computations though. Now, radioactive decay problems are a lot of fun. In Chernobyl, they dumped quite a bit of plutonium-239, unfortunately. Suppose 10 grams of plutonium-239 was released during the nuclear accident. Now, I've just told you at t equals 0, I had 10 grams of material. So my first point is 0, 10. How long will it take for, so I'm looking for the time for the 10 grams to decay to 1 gram. So I'm going to want my final amount to be 1 gram. If the half-life of plutonium is 24,100 years. Okay, so the half-life is 24,100 years. And how much will be left? If I start with 10, what's half of 10? Well, 5. So now I can go back to my formula. Y equals e to the kt. At, let's see, 0, 10. I have 10 is equal to, oops, forgot my c. C, e to the 0, so c is equal to 10. Good going. So I know I have the equation y equals 10 e to the kt. All right, now I know at 24,100 years, I've got 5 left. So at 24,100, I'm at 5. So I've got 5 is equal to 10 e to the k, and my t is big, so don't worry about that. Solving this for k, I get a very small negative number. That's all right. 0.1234 zeros, 28761. Now carry all these extra digits along. So my formula is y of t is equal to 10 e to the minus 0.123428761t. Now I'm looking for how long until it is down to 1 gram. So I'm looking for t. So 1 equals 10 e to the minus 0.123428761 t. And when I solve this, I wind up with t is about 80,059 years. That's one of the reasons plutonium is so nasty. Now, we also do population studies. Suppose you have an experimental population of fruit flies. It increases according to the law of exponential growth. Great. There were 100 flies after the second day. So my time is 2 days, and I have 100 flies. After the second day, and 300 after the 4th day. So I've got the 4th day is at 300, and I'm looking for the initial population. So I'm looking for 0c, because that's, of course, my initial value. Okay, I know I have the equation y equals c e to the kt. Now let me show you a trick. I love tricks. When I have these two but I don't have the 0, go on and write them out. So I've got 300 is equal to C e to the k times 4. Now write the second one. 100 equals C e to the 2t. Now, none of these are 0, so we're perfectly okay dividing these two equations. Okay, see, when I divide those two equations, I'm going to lose C. That should be a K, not a T. Sorry about that. So this is 3 is equal to e to the 2k. Kind of slick, isn't it? So when I solve this for k, I get k is about 0.5493. Now, in order to find c, I can pick either point. It doesn't matter. Let's look at the point 2, 100. So at 2, 100, what have I got? I've got 100 is equal to C e to the k, which is 0.5493 times 2. Solving this, I get C is about 33. They're whole flies, so don't give me any half flies. So my initial population is 33. Okay, you give this a go. Stop the video when you're done. Good luck.